Hello, everybody. My name is Arun Prakash, and welcome to C595, my submission Elasticity. I'm going to send out these few syllabus. You take one and pass the link back. Is that too dark? Okay. Let's see. Okay. Those of you who are sitting on this couple of tables, maybe if you want to, push back a couple feet, and if you can move back here. Just so that, try to arrange yourself so that you can see the board, the screen. Okay. So let me just briefly go over the syllabus. So my contact information is given here, and maybe I'll talk a little bit about myself. So most of you or some of you might know that I joined Purdue last semester, and before that I was a lecturer postdoc at UCLA for a couple of years. I did my PhD at Illinois, and my research is mostly about computational mechanics. So finite elements is really near and dear to my research. So that's pretty much about me. Let me just briefly try to get an idea of you all. So how many of you are in civil engineering? And how many of you are in structures? Any other areas? Geotech? Some geotechs? Water resources, hydraulics? Okay. Any mechanical engineering students? A couple of mechanical. And anybody else missing? Ag engineering? Okay. All right. So that's the introduction. I've already set up a course web page on Blackboard, and I also send out an email. I set up a class list also. So did you guys get the class list email? Okay, that's great. So let me briefly go over the Blackboard course web page that I set. So the copy of the, so this is the main page of the course web. There's a link to the syllabus. I'll be posting homework solution under this, and there are two modules, quote unquote, for learning modules. They're called on Blackboard. So this one is for the course books that are available through the Purdue libraries. Purdue libraries has a lot of files which you might have to download one by one, a lot of PDF files. So here I've just put all of them together all in one place for you, the course books that we'll be using in this course. I'll also be posting some sort of lecture summaries. So whatever I'm going to use the tablet PC and I'll write on the screen. So whatever I write, I'll post on this lecture summary. But you keep in mind that this is just a lecture summary. So I'll just list out mostly, I won't be writing out entire notes for you. So I encourage you to take lots of additional notes as you go along with the lecture. And finally, there is this discussion section that I'd like you to use. So when you're solving homework problems or you come across any questions or thoughts about the material in the course or the homework problems, you can just go and click here. And there's one sample post that I just created here. So you can click on this create a new message and you can post your question here. I might answer. I also encourage you all to answer each other's questions, try to collaborate that way. So this is pretty much the course website. I'll also be using the gradebook, online gradebook here. So if you click on this link, My Grades, you should be able to access all the grades that you have up till that point. So back to the syllabus. Here's a little bit of a description of the course, but there's a detailed list of the topics if you turn over on the second page. But I'll go over those detailed lists in a little bit. But let's talk about first the prerequisites for the course. How many of you, so the official prerequisite that is listed is C474. So hopefully everybody has had some advanced structure analysis and or an equivalent course. But how many of you have not had the CE570 course? Okay, so there are a few of you. This would be a good course to, a very good prerequisite for this course, but depending upon your background and your understanding of basic vector calculus and some solid and structural mechanics, you might be able to, I think you should be able to continue in this course and be able to understand the material. But just in case, take a look at some of the material from that course also. So in addition to that, how many of you have never had any programming experience before? Great. So everybody has some programming experience. How many of you don't use MATLAB that much? Okay, so that's going to change because you're going to use MATLAB for programming in this course. The reason we are choosing MATLAB is because, first of all, it's a very friendly, quote unquote, for beginners. There are obviously much more advanced programming languages, but in the case of MATLAB, you don't have to worry about things like coding up a solver, coding up input and output subroutines for finite elements, those kinds of things. So MATLAB is a convenient choice, but if you still want to continue using some other programming language, then by all means. So in addition to that, we will briefly introduce to you one of the softwares, Abacus. And how many of you are actually familiar with some finite element software? Okay, not many of you. So that's good. We'll use, to a limited extent, Abacus. This is not a class about where I'm going to try to teach you how to use Abacus. but you need to know what are the capabilities of standard finite element software like Abacus. And there's others also, ANSYS, LS-DYNA, there's quite a lot of other softwares also. The choice of the software is up to you, but I recommend that you download this Abacus student edition. So if you click on this link, it will take you to a website where you will have to register as a Purdue student, and then it'll allow you to download the software for free, so that you can install it on your laptops or on your home computer, and then do small problems or homework assignments using that. One limitation of this student version is that it will allow you only very small problems. So something like 1,000 nodes, which means you cannot model anything realistic. So if you want to model some real life problem, then you would have to go to one of the ECN or the ITAP labs. There's one in 1212 in civil engineering. It's open 24 hours, 7 days a week. So especially for the final project, I would expect that you would make some sort of a reasonable sized model, and to be able to analyze that model, you would have to use the full version of the Abacus. All right. Any questions so far? Okay. So the grading basis is fairly even. I'll be assigning almost one homework every week for a total of maybe 8 to 10 homeworks. And then in the latter half of the course, I'll assign a term project. So as you can see, there is no final exam. This final term project is in place of the final exam. But there's going to be 2 midterms. So please mark your calendars also, February 22nd, Monday, and April 12th, Monday. The timing and the venue might change a little bit here and there, so I'll send out an announcement for that too. So yeah, one thing you can note here is that the second midterm is pretty late into the semester. So this is April 12th, and only 2 weeks after that you will have the final exams. So this is some sort of even a replacement of a final exam, but I don't want you to be preparing for the final exam and doing the project in the last couple of weeks. So at that time, this might work better. Okay. So if there's any conflicts or anything with the timing of the exams, let me know. On the homeworks, obviously you all have to submit your own work. Collaborating is okay, but copying is not okay. So you are encouraged to talk to your friends, even on the discussion forum, use different sources. But in the end, you have to have some sort of a litmus check. And one check that I recommend is, after you are done with the homework, go back and take a look at it and ask yourself that if I were to ask you the same problem on an exam, would you be able to do it all by yourself? So if the answer to that is yes, then that collaboration is good. Okay. There is one announcement about the emergency procedures. So if something major happens on the campus, then I'll send out an email and let you know how to proceed with the grading and all that stuff. All right. So any questions till now? Okay. So I'm not going to go over in too much detail on the list of topics, but what I intend to do here is try to point out some basic features that are available, or basic features of any finite element formulation. So what we're doing here is I'll go over a little bit of a review of elasticity in the next couple of lectures. And the rest of the course is pretty much one-dimensional boundary value problems, which is some sort of a tryout of basic finite element concepts. So one thing I'd like you to note here is, any finite element formulation follows these steps. You start with a governing differential equation, which is also called the strong form. You express or that strong form in an integral way, and that is called the weak form. And those of you who took 570 might be familiar with the principle of virtual work and that way of expressing the equations. An alternate weak form can also be obtained using what are called variational principles. So these variational principles, whenever you hear the word variational, immediately try to think of energy methods. Right. So those of you who have not taken 570, or if you go back and try to remember what you did in structural analysis, you might have studied energy methods. So as soon as you hear the word variational, the word energy methods should come to your mind. And once you have developed a weak form, either from the principle of virtual work or using an energy method, then you discretize the problem. And discretization is pretty much the heart of all finite elements technology. What works, what doesn't work, this is all based in discretization. And after that, you just, and this discretized version is called the Galerkin form, and you can solve the problem and get an approximate solution for that. So the rest of the course will do similar topics, but in 2D and 3D. I'll talk a little bit about dynamic problems and time stepping. So how many of you have had the course last time, I guess, Structural Dynamics 573? Okay, so there might be some overlap here with that. And the last two topics would be beams and frames and plates and shells. If we get time, we might also go into some advanced topics. So these are pretty much the list of topics. Any questions or concerns about this? Okay. So here are the textbooks that we are going to be using primarily in this course. And so how many of you have already bought the textbooks? I think I have listed these two as the textbooks. So not many of you have bought the textbooks. So here's some information about this. This one is one of introductory finite element books, and as you can see, it's a little bit more expensive than the rest of them. So depending again on your understanding of the prerequisites, if you're not able to understand what's going on in the class, then I highly recommend that you get one of the basic introductory books and try to follow along in the course in that. These first three books, we are not going to use all three of them. This is a 3-volume set, and this set by Zinkiewicz and Taylor, this is one of the most comprehensive books that's been written in finite elements. But again, this is not some sort of a textbook or an introductory book. This is a very good reference book. So once we are done with the lecture, you can go back and take a look at the same topic in these books, and I will point out the sections in the books. And actually, if you take a look at the list of topics, I do point out the particular sections or the chapters in the book that I'll be drawing the material from. So this is the introductory book by Reddy. This is one of the more comprehensive books, which is still easy to understand, not too difficult. And the last one by Hughes. This is a little more advanced book, which talks a little more on the mathematical theory of finite elements. So this is not some laid back, light reading kind of a book. You really have to work with the book to try to understand what's going on. So like I said, I won't be following any of these books to the word. I'll make up my own notes, and I encourage you to take notes in addition to all these books. And I'll point out the sections, assign reading assignments from these things. Okay. So this, for those people who haven't taken 570, this was the book that this is a very good prerequisite book for this if you want to understand solid and structural mechanics. And this is also available for free through Purdue Libraries. I've already uploaded it on the Blackboard. If you go under Learning Modules and Course Books from Purdue Libraries, so there are all these 4 books that are listed here. You can just download all of them, and as needed, you can print out the particular sections. All right. So obviously, there's a lot of other books also. If you are able to obtain any of these introductory books, that might work for you also, in case you don't want to spend $150 on the Reddy book. But there are a couple of very good books on nonlinear problems, and the first one, this book by Bonet and Wood, in my opinion, it's one of the best books for nonlinear problems. And if you want to understand, or if you want to study nonlinear structural mechanics. And then there's a whole list of books on the mathematical theory of finite elements. All right, so that's pretty much it about the syllabus. Any questions about any of the topics? Okay. So what I'll do is try to introduce to you some basic material today, and all right. So is this visible from the back? Especially, I guess, that corner and this corner. Okay. So what I'll do today is some introduction, finite element from from a little bit of a historical perspective. How was it developed and that sort of things. Talk about a specific application and other application areas that that finite element is used for. And then if we get time, we will also talk about vectors and tensors. So how many of you are not familiar with tensors? Okay. All right, so the reference material also for this, let me list out the reference sections. Zienkiewicz and Taylor, that's Z and T, volume 1, chapter 1, or you can also take a look at the chapter 1 from Reddy's book. All right, so let me first start by laying out the objectives of the course. So one primary objective of the course is that you should be able to set up a problem mathematically and be able to derive the finite element equations given a strong form or given the governing differential equations. So formulate the problem mathematically, and derive finite element equations from that mathematical form. You should also be able to use modify as needed existing finite element software. So for example, the software that I was telling you about, Abacus, it has facilities for you to be able to add your own material type to it, or your own element type to it. And we'll talk about that later in the course. And another objective of this course is that you should be able to read and understand some basic literature, papers and journal papers, conference papers, that kind of thing, and be able to reproduce the results mentioned in the paper. So this is sort of related to your final project that I have that I'll assign later in the semester. And so for the term project, if you're already working on some sort of a research problem, you're welcome to try to formulate a research or term project around your research problem, and you can use that as in this course. Otherwise, I'll probably assign a list of papers that you can go through, take a look what you like, and then read the paper and try to replicate the results and critique about that paper. So that's trying to get at the scientific method, right? That if you whatever results are reported in the literature, you should be able to reproduce those results. Okay, so these are the broad objectives of the course. And so what is finite element? Let me try to sort of give one not a definition, but some sort of a introduction to finite elements. So broadly speaking, it's a method of analysis and design. It's a tool for analysis and design, and it's one of the best tools available to engineers these days. And what that tool allows you to do is to get approximate solutions to a wide variety of real-life problems. So it's one of the best tools for analysis and design. Of common physical systems. So these physical systems could be a structure, could be an automobile, could be a spacecraft, could be a submarine, could be a foundation system, tunnels, whatever, right? But there's a caveat. So even though this is one of the best tools available, the caveat is that the computed solution from the FE method always has some errors. And what I'm getting here is that it's an approximate solution. So let's let me talk a little bit more about what are these types, what are the types of these errors that we commonly encounter in finite elements. And let's talk about that using an example. So let's consider this building that we are sitting in right now. If we were to try to analyze what types of loads, what type of deformation, what type of behavior this building will show under a given circumstance, some sort of loading, then how do we go about trying to solve that problem? So let's say this is my real life um system. In this case, I'm assuming it is a building. And the first step in any analysis, and specifically in finite element analysis, is to be able to classify that into a mathematical model. So any real life problem, you have to first try to formulate it in terms of a mathematical model. So all these beams and columns you try to model with either beam theory, or you can also use continuum solid mechanics to model all of these structural members of this building. So the errors that you make in here are physical errors. Um, your your mathematical model may not represent the real life problem exactly, right? So some of the errors here, the mathematical models that we are talking about is basically structural and continuum mechanics, and you can rest assured that a lot of people have developed these theories over a very long period of time. So these theories are very well formulated, and there's very little errors in these in the step in the description of the mathematical model. But one big source of error is the way we try to characterize material behavior. So the major source of error here is material behavior. And as you might have already studied, most of the material models that we try to use are small strain, linear elastic. And obviously, as you can imagine, there is no material in the world, in the universe, that behaves in a linear elastic way, right? If you push the structure, or if you push your system to a little farther extent, nonlinear behavior will come in, fracture processes will come in, all those different kinds of errors, they're all lumped into this physical errors. So from the mathematical model, let me just say that this is either solid or structural mechanics. And from here, you do a discretization. So what you obtain here is a discrete numerical model. So an example of this kind of a model would be your finite element mesh, or if you've been using structural analysis programs, then all the models that you use for doing structural analysis, those kinds of models would be listed in this layer. And the major error that comes in when you do a discretization is truncation error. So I was telling you about these mathematical models. Now, these mathematical models, they are all at a continuum level. So there's nothing discrete at this stage. But when you take your mathematical model and divide it into small parts, that's a discrete numerical model. And truncation error is something that should be familiar to you when we use Taylor series approximations. When we use Taylor series, we chop off the rest of the higher order terms, right? We keep the first or maybe the second order terms, and we chop off the rest of the terms. So that's truncation. That's truncation error. From the discrete numerical model, you also go and implement it into a computer. So let's say computer implementation. And this will give you an approximate solution. So here, the error that you make is called round-off error. We all know that when you write a computer program, the computer has only a finite amount of digits that it can carry. So whatever it is losing in terms of significant digits is called round-off error. You might think that these days we have computers that can carry up to 4 decimal places, and nobody needs those 14 decimal places, and nobody needs the answer accurate to that level of 14 digits. But what happens is when you build this discrete numerical model and when you try to invert that system of matrices, the accuracy of your solution depends on something that's called the condition number of that matrix. And the condition number, the round-off errors in that, the inverse of that matrix can be very, very high. It may not be accurate to all your 14 digits. But in addition to this, there's a lot of other errors that also might creep in. This is the sort of the regular types of errors. One of the major sources of errors in finite elements is user error. So you're trying to get to an approximate solution through all these 4 layers of smoke screens, if you will, right? And it's kind of like playing darts. So if you have a point somewhere and you're throwing a dart, and you might hit the bullseye or you might not. But if you hit the bullseye within 10%, that's our engineering accuracy, a measure of the engineering accuracy that we want. Then we say that okay, we'll accept that approximate solution, and we'll go on. But how do we know whether we've come within that 10% accuracy or not? So to judge that, you have to be able to understand what are the capabilities of finite elements, and what you can and what you can't do. So if you're not careful about that, that's the major source of error that you get. So let me mention a couple more things here. So whenever you develop or whenever you use some sort of a computational tool, 2 words are commonly used, something called verification and validation. How many of you have heard of that before, verification and validation? Okay. So the first step here, starting from a real-life system, going to the mathematical model, to make sure that our mathematical model is correct, what we do is called validation. And validation through experiments. So anytime we we build some computational model, we have to validate it. Anytime we build some mathematical theory, we have to validate it. If you develop some new material law for concrete, for steel, or for any other material, you have to be able to conduct some experiments and make sure that what your mathematical model predicts is actually accurate. And the second one that I mentioned to you is verification. So this is validation and this is verification. And this is done through quote unquote exact solutions of the mathematical model. And what I mean by that is that now that you've come up with a mathematical model for your real-life system, there are a set of simple problems, let's say one-dimensional problems, a beam problem, or a simple frame problem, for which you might be able to solve the equation exactly. So all these mathematical models, they are just differential equations. And for simple systems, you might be able to solve those differential equations exactly without having to use computers and all that stuff. So this gives you a good way to check whether your discrete numerical model, whether the finite element model predicts the exact solution. And the reason I'm saying exact in quotes is because this is not really the exact solution of the original problem. This is the exact solution of the mathematical model. Okay. So that's pretty much a word about errors. And once again, whenever you use finite elements, you have to be very careful. You'll get some number out of your software. If everything goes well, you'll get some number. And it's up to you entirely to try to judge whether that number makes sense or not, whether this is reasonable, and then you have to be able to find ways of being able to verify your solution. Okay, so any question on this? This is just some general introduction stuff for finite elements. So let me briefly, I think I have 5-10 more minutes, briefly introduce to you the finite element from a historical perspective. And instead of talking about that, what I'll do is use this table that is also available in your books. So this is a table of summarizing how the finite element method evolved and who were all the different contributors. So this, I think the print, the size of the font is probably too small for you guys to see in the back. Is it visible or not so much? Okay. Let me see if we can zoom it up a little bit. Hopefully that is a little better, but we'll try to figure out something for this. So finite elements was traditionally actually developed by structural engineers. That's what this line towards the left, all the structural analysis programs that people developed in the 1930s, 1940s, finite elements was born, the term finite elements and some theory also was born there. But people had been using similar ideas in mathematics much earlier. So these are the two lines of development that people usually talk about in developing finite elements either through engineering or through mathematics. So from the mathematics side, people were trying to figure out how to solve all these complicated partial differential equations. So one of the methods that was developed early on was finite difference methods, and then recently the finite difference methods were also formulated in terms of what is called a variational finite difference. So again, whenever you think of variational, what it means is an energy approach, energy method. And here is the uh, the heart of how even we are going to approach finite elements. You can take your governing differential equation, which is nothing but an equation of equilibrium. So does anybody remember what is the equation of equilibrium from mechanics? Divergence of div s plus b. Does that ring a bell? Okay. And we'll talk about that next time also. So that is a differential equation that we are trying to enforce. And to solve that equation, you can either use the method of weighted residuals, that is your principle of virtual work. So weighted residuals is nothing but your principle of virtual work. Or you can take an energy approach. And in both the cases, you will end up with the same mathematical model, which you then discretize using finite elements, and then you solve solve your discretized mathematical model. So a couple of things that I'd like to add here are, how many of you remember from maybe structural analysis Castigliano's theorems? Has anybody heard of that? So this is Castigliano's theorems are also related to energy methods, and so there is a tie between this structural engineering approach and this mathematical variational methods, and that tie comes from Castigliano's theorems. There are other theorems also that we use in structure analysis called Bette's law or Maxwell's law. Anybody heard of those? Okay. So those are sort of the ties that are available between structural engineering and variational methods or energy methods from a mathematical perspective. One quick word here about the term itself, the finite element. It was first coined by Clough in 1960. How many of you have used the book by Clough and Penzine? Okay, that's one of a very basic or a good book on dynamics of structures. So it's the same Clough who coined the term finite element, and then a couple of other people worth mentioning here are Bruce Irons, who is credited for something called the patch test and the isoparametric finite elements. And there's a lot of other people. The list just goes on about the who's who of finite elements. So let me not go into that. I'll probably miss a lot of people there. But so we didn't get through quite as much as I wanted to. But next time, what I'll do is I'll set up a sample application problem of, let's say, a bridge, and show you the different steps and where finite element fits in and how you can use these kinds of techniques. All right, so I'll assign a homework problem on Blackboard. this week, not today, maybe tomorrow or day after. And that homework problem will basically try to make sure that your prerequisites are in order in solid mechanics and maybe some vector calculus. Okay. All right. So see you Wednesday.